talk of the morning before lunch. So we have Lisa Masserova. She joined the CBI Fellows last year in the area of security and privacy, working with Professor Elaine Shi. Her research is in applied cryptography, privacy, and security, with the goal of creating a future where privacy-preserving technologies become standard across industries, including finance, healthcare, and public policy. And I really hope that that goal is achieved very soon. Towards this goal, her work contributes to development of secure, scalable, and practical cryptographic systems that empower individuals and organizations to collaborate without compromising on privacy and security. Today, she'll be presenting her work on non-interactive, publicly verifiable zero-knowledge proofs for fair decision trees. Over to you.
Yeah, thank you so much for the introduction. We will be talking about AI, and this work specifically is with my amazing collaborators, Antigone and Akira. Okay, so as we all know, the AI is nowadays being used everywhere, from virtual assistants to determining the creditworthiness of people. And however, such widespread usage also has its risks. In particular, as probably everyone in this room knows, machine learning models have the potential to harm people by reinforcing existing biases in the society. And to counteract this, regulations are being currently drafted all over the world to ensure that AI is designed with anti-discriminatory principles in mind. For example, in the EU, the AI Act has been recently adopted, and the corresponding measures and policies are currently being integrated step by step, starting actually like in February. And in the US, the Colorado AI law, which targets high-risk AI systems, for example, those related to financial services, will go into effect in next February. Now, even given this regulation, fairness in AI is a very complex problem, and before I explain our use case, I just want to point out that we do not claim to have solved the fairness problem, in the sense that we don't propose any new notions, nor do we claim that the notions that we are using in this work are the right ones. Instead, with our protocol, the model holder will be able to prove in a privacy-preserving way that a model satisfies one of the standard fairness properties. Specifically, we will focus on the demographic parity and equalized odds. And if you have suggestions for any sort of notions that we should consider instead, please let me know. I'm very open to feedback here. Okay, so let me introduce our setting. Say we have a company, for example, Bosch, which has trained a model. And this model is very valuable, and hence the company wishes to keep it private. At the same time, Bosch wishes to prove to a third party that this model satisfies certain fairness metrics on a given public test dataset. This third party can be a customer, it can be an external regulator, it can also be some different team inside, for example, Bosch itself. And the obvious way to do it would be to send the model to the verify and clear. However, there are obvious problems with this, because first of all, clearly the verifier learns the model, so there are no privacy guarantees whatsoever. And second, perhaps slightly less obvious, each third party that wishes to perform the fairness check would need to perform this verification from scratch by themselves. So can we do better? Can we somehow allow the verifier to check the fairness metrics without sacrificing the privacy of the model? And even more specifically, can we allow it to check fairness properties without learning anything else about the model, apart from the fact that the model is actually fair, given this test data set at least? And further, the goal would be to do this in one shot, meaning that we will provide a sort of non-interactive certificate that every new verifier would be able to check by themselves without sort of the interaction with the approver. Okay. And in our work, we answer this question positively. So for this, we will focus on specifically decision trees on the machine learning side and use a primitive known as zero-knowledge proofs on the cryptographic side. And I believe most in this audience are probably familiar with the decision trees, but very briefly, you can think of a decision tree as a model where a set of questions are organized in the shape of the tree, and each leaf node contains a prediction. So to obtain a prediction for a given input, you would simply follow the path from the root to the leaf while checking whether the condition is satisfied or not. And on the cryptographic side, we will rely on a well-known primitive, namely the zero-knowledge proofs. And in such proofs, there is one party, the prover, who holds some secret data and wishes to prove to another party, the verifier, a certain statement about this data. The idea is that these two parties engage in an interactive protocol, and by the end of it, if the prover was indeed showing a truthful statement, the verifier will be convinced. But at the same time, no information about sort of like the data or like the secrets of the prover, apart from the statement being true, are leaked in the process. And this maybe sounds a little bit like magic, but this indeed can be done. And to give you an idea how, let's take a small detour and imagine the following situation. So let's say that there is a magician who claims to know how to quickly count the number of leaves on any given tree. And this magician wishes to prove to a child that he has this ability. As we all know, a magician never reveals its secrets. So how could the child possibly verify the statement? Well, the child can start by first picking some random tree. And now the magician could tell the child the number of leaves on this tree, but the child obviously cannot verify whether this number is correct or not. However, what the child can do is the child can ask the magician to turn around, and while the magician is not looking, the child can decide to pick or not to pick a leaf from this tree. So to remove or to not remove the leaf from the tree. And now the magician can turn around and tell the child again the updated number of leaves on this tree. If the magician indeed knows how to count, then this shouldn't be a problem, because the magician will simply again count the number of leaves and just give the child the updated number. However, if the magician is lying, then the magician can presumably only guess whether the child decided to pick or not to pick the leaf from the tree. And so with probability 1/2, a lying magician will be caught, because the child obviously knows what it did. And they can repeat this process multiple times to further decrease the probability, to further increase the probability of catching a lying magician. And using this process, after some time, the child will probably be convinced without the magician revealing his method of counting. And obviously, this is a made-up example, but hopefully it gave you some kind of intuition for how these proofs can work and how they can provide concrete mathematical guarantees about the validity of the statement without sort of like releasing any information on top. So coming back to our scenario, we will use zero-knowledge proofs to have the company prove the fairness property of its proprietary model to a third party on a given public test dataset. And we will rely on the key properties of zero-knowledge protocols, specifically correctness, soundness, and zero-knowledge. Okay, so for this, we will have the company first commit to the decision tree model. And you can imagine this commitment as sort of some black box, which contains the tree, but completely hides all the conditions and all the sort of thresholds and basically any information about this tree, apart from the fact that this is indeed a decision tree of a given size. And given this commitment, the company will sort of prove, or like will want to prove, that the fairness metric for this committed tree on a given public test dataset is above a certain value, let's say above 0.8. If this is indeed the case for the committed model, then by the correctness property of the zero-knowledge proof, after the prover and verifier interacted, the prover will be convinced by the statement. However, if the fairness outcome was actually 0.65, but the company nevertheless wanted to cheat and claim that the fairness was above 0.8, then by the soundness property of the zero-knowledge proofs, when the verifier will check the proof, it will not pass. And finally, by the zero-knowledge property, this property will prevent the verifier from learning anything about the model apart from the outcome of the fairness. Okay, so in terms of prior work, there are a lot of works on fairness, but they do not provide privacy guarantees. And one exception, for example, is the confidential profit paper that was published at ICLR last year. In this paper, a decision tree was trained in a fair manner, and then zero-knowledge proofs were used to sort of show that a certain fairness condition holds in each intermediate node. And our insight was that, well, all the standard fairness metrics that we saw, like usually they only consider the outcome. And so we can actually skip sort of like proving fairness for each intermediate step and considerably improve the efficiency. So specifically, for example, if you look at the demographic parity, which intuitively says that the results of the model's classification should be independent of the sensitive attribute, you see from this definition that this unfairness value that you're computing is computed based only on the outcomes and whether the inputs belong to one sensitive class or another, but it does not concern itself with the internal dealings of the model. And same holds for the equalized odds, which states that the model should predict the outcomes equally well for all values of the sensitive attribute. Okay, so let me give you a short overview of how our protocol works. So we will first train a decision tree model, and this is done without cryptography. And then once the test data set is known, the prover will compute the output and calculate the fairness metric. And finally, the interesting part is that we will prove that the output satisfies the fairness property, and this final step will be done in zero-knowledge. And the good thing about our protocol is that it has the so-called public coin property, meaning that according to the protocol, all the messages that are being sent by the verifier are actually chosen uniformly at random and are also independent of the prover's messages. And this is a very useful property because it allows us to easily transform an interactive protocol into a non-interactive solution using the Fiat-Shamir transformation. And at a very high level, so the idea here is that with the sort of, instead of having the verifier send these random messages to the prover, what the prover can do is the prover can simply compute this randomness by themselves using a cryptographic hash function, which will be applied to sort of all the public information and all the sort of elements of the prover's transcripted up to the point that the corresponding random message needs to be sent by the verifier. And this will allow us to actually obtain a one-shot non-interactive certificate that will later be verified by how many verifiers you would like to have. And we have a few other optimizations in our protocol. For example, we show how the prover can use a sort of random subset of the test input data set to, again, improve efficiency and not have to use the entire test data set while still providing formal security guarantees. Okay, and as you are now probably interested in, we have a few implementation results. So as you can see, there is a one-time, so we have, okay, first of all, we have a one-time setup phase, which is required for the zero-knowledge proofs. And the setup phase and the prover times are both below 2 minutes. And the prover time itself is just 1 minute. However, the probably more important column here is actually the verifier time, because the prover will actually only need to generate this proof only once, right? But maybe like there are different verifiers, so like presumably the verification algorithm will be run by multiple parties, and presumably this is actually like slightly more important here. And the verifier time is actually below 1 second, and the proof size, which I guess is also pretty important here, is only 0.2 kilobyte. And I guess the other interesting question is how it compares to prior work. And here you can see a comparison of our work with the confidential profit. First of all, as you can see, the confidential profit actually did not have a setup phase. However, their protocol is not sort of publicly verifiable and non-interactive. So for them, they would need to sort of execute, for example, the prover's algorithm multiple times with different verifiers if there are different verifiers that would like to check fairness. And as you can see, so we have checked the how, like, for example, this is for the equalized odds. And we check this on different data sets, so specifically on the default credit data set and the census income data set. Our protocol actually concretely outperforms the confidential profit in terms of the verify time. So the verify time improved by, I don't know, a factor of like 70 up to 100, I guess, depending on the size of the test data set. Here you can see the size of the test data set. I'm not sure. Okay, yeah, you can see my cursor. And what I think is more important is the prover size, or like the size of the proof is considerably improved. So the size of the proof was actually about I don't know, like 100,000 kilobytes for the confidential profit, and yeah, and like only 0.2 for us. And yeah, I think this is actually very, very important. I do have to say that yeah, the prover time is about a factor of 10 larger than the confidential profits, but yeah, as I mentioned before, we will only need to execute it once, whereas in confidential profit, if you would want to prove this to multiple verifiers, they would need to re-execute the algorithm this amount of times. Okay, so in terms of takeaways and future work, our protocol allows to prove that a trained decision tree model is fair. And during this protocol, nothing is released about the model except for the fairness metric, or the fact that the fairness metric is above a certain threshold. And we are able to produce a one-shot certificate, meaning that if there are multiple verifiers, then they can all sort of use the same one-shot certificate to check, and they will be convinced by the certificate. In terms of future work, it would be interesting to enable private test data sets, meaning that maybe the verifiers should be able to supply some test data on which they would like to check the fairness, but they would also like to have some kind of guarantees that this test data in fact remains private. And this would require actually a few, I believe, completely new ideas on the cryptography side, and maybe some ideas from multi-party computation would be useful here. And the other obvious one would be to extend this to different machine learning algorithms. So the first thing to do, I guess, would be to extend this to XGBoost. And yeah, finally, it would be also interesting to maybe like not only look into fairness, but let's say also accuracy for some other important properties. Yeah, that's pretty much all I have. Thank you for your attention. And if you have any questions, yeah, they're more than welcome.
Question?
What's the scaling of this, like, with data size? Like, if you were to take it up to like 1 million points, is it like linear scaling, or is it like super linear?
Data size of what exactly?
It's like the number of I guess the n in that setting.
Yeah, this is the number of test data sets.
Yeah.
So I mean, okay, so like our proof size will remain succinct, right? I guess one thing that you need to be like a little bit careful with is that so like we used a lot of RAM for this. This is actually because of n. So if your n increases, then you would actually like need to like use a lot of RAM because of how the zero knowledge proof system works. One interesting thing that we did was we sort of like this m is the size of the random subset, right? So I think a reasonable thing to do, or like at least we as cryptographers thought maybe this is actually reasonable. We would hope that maybe machine learning people could verify this, would be to select a random subset of this test data set and to only run the algorithm on this specific subset, right? While having the guarantee that the prover was actually not choosing this subset maliciously.
That's a great idea. Thank you.
Mm-hmm.
Maybe just to clarify, so how do you, so for this random selection, how do you guarantee that that it has actually been selected randomly for subset selection and not maliciously?
Okay, so like I guess I mean, like one thing that you can do is to basically like, okay, again, like apply hash function, right, to the whole like public desk data and everything, and based on the outcome, select like this specific index. Like let's say like the first, I don't know, like the first like 30% or something like this.
And also, so I'm guessing that the proof uses specific properties of decision tree for this, right? So I mean, extending this to other, I mean, XGBoost or maybe even actual deep learning networks, right? Do you see? I mean, how do you see this scaling? I mean, is there new tricks that you'll have to find, new cryptographic tricks?
Yeah, I feel like you would need to have some kind of like new ideas on the cryptographic side because, yeah, I guess like the interesting part is sort of the commitment. So like this one also like uses the fact that this is kind of like a decision tree, right? And so like you commit, you can like sort of like improve the efficiency by committing to the decision tree in a specific way, right? If you have some kind of like very large models, then you would also like need to think how to do it like slightly differently, maybe.
Hi, it was a great talk. In your next steps, you mentioned like exploring other properties. What kind of other properties, valuable properties, would you be interested to?
Yeah, I guess like accuracy would be very interesting. Then maybe, I guess like what I heard at least a lot of people are interested in is some kind of like explainability, right? So I'm not like super familiar with that, but maybe this is also something that would be interesting to look into. And yeah, I mean, I'm also very, very open to suggestions here. So if people who have more machine learning knowledge than I do want to provide some input, then that would be awesome. Thank you.
Okay. Any other questions, Lisa? If not, then let's thank the speaker again.